All right, so yeah, I want to introduce some material for next class, so for the next two papers, and then this material is going to be about inverse reinforcement learning. So that might sound weird, but it's actually a very useful technique, and we're going to see in particular in the context of both robotics and autonomous driving, where this is an approach that has been quite successful. Okay, so let's go back to what is reinforcement learning. So if you recall, this is our abstract pictures of what a reinforcement learning agent does. So right, it executes actions, it influences the environment, and then the environment will produce some state and some rewards that will inform the agent about how well it's doing, right? And as we've got this loop, and then the goal is to find a policy pi that maximizes the rewards. Okay, now inverse reinforcement learning, the setup is slightly different. Now we're going to have an expert, not an agent, but an expert here. This expert is going to execute some actions, and the idea is that this expert should be executing a very good policy, ideally an optimal policy. Therefore, the actions are going to be good. They're going to be optimal actions, or at least actions that we want to perhaps select as well. They're going to influence the environment, and then the environment is going to produce some states that the expert can receive and so on. And you'll notice that I've grayed out the reward because in this setting, either the rewards are simply not observable to an observer outside, or even for the expert, it might not be obvious what are the rewards. So in several settings, what happens is that the rewards are really meant to be the objective that we would like an agent to optimize, right? So that's how we specify the goals in a task. And then so in various problems, especially in robotics and autonomous driving, there you might be in a situation where for autonomous driving, you would like to have a car that maybe is efficient, is safe, will provide a smooth ride, so you can think of lots of possible objectives. And now, if you think about it, every day, everyone here presumably is driving, and then we are driving according to our own policy, but then we might not have an explicit way of specifying what are our objectives when we drive. I mean, we would all agree that we try to drive safely. We try to drive in a way where, you know, the car is going to run smoothly, and, you know, we won't brake suddenly and have some jerks and things like that. And we try to be efficient, presumably as well in how we drive, right? But then how exactly we trade off these different objectives and what is our formal objective, we don't really have one, or at least it's not explicit, right? So there's a lot of situations like that where the rewards that are being optimized, either they're just not observable or they're not explicit, and that's why here I've grayed this out. So now the goal is going to be, in fact, to find the reward function that the expert is implicitly optimizing. So this is where the name comes from. So inverse reinforcement learning, because now the goal is to find the reward function as opposed to finding a policy. We're going to see in a few applications why this is interesting. But here you see, if you have an expert that's already executing some actions that are presumably good, right, then we essentially have the policy, or otherwise we have some demonstration that tells us what are the optimal actions, or otherwise some very good actions in lots of states. And that's why here the goal is not so much to find what is the optimal policy, but instead to find the reward function. Okay, and so that's why this is called inverse reinforcement learning. And then this will be very useful in settings where you would like to teach an autonomous system, often a robot or self-driving car, based on expert demonstrations. Okay, so classic applications in robotics. If you would like to train a controller to follow some trajectories, and then perhaps these trajectories, they can be obtained by a human expert who would demonstrate how to perform a certain maneuver, then you can use these trajectories to then perform inverse reinforcement learning. So try to obtain an implicit reward function and also a policy based on that. So this was done, so I've got here some applications, so some examples. This is not a complete slide that does not acknowledge all the work that has been done out there, but I've got a few of them. So in particular, for helicopter aerobatics and also quadruped locomotion. So again, in robotics, it's difficult to specify based on the mechanics and the physics what is the model and what might be the goals and so on. But you might be in a situation where the type of robots you have, especially if it's a humanoid robot or if it's a robot where you can get something else to demonstrate what should be the solution, then it'll make sense to use inverse reinforcement learning. Okay, the other common application is autonomous driving. And here we have humans. I mean, everybody in this room presumably could be a driver, right? So we are already expert at this task. And now, instead of trying to program a self-driving car to perform certain maneuvers in various ways and specifying some objectives and so on, why don't we simply feed the self-driving car with some examples of how humans do drive, and can we learn from this, right? So that's another important application, and this was done in the context of highway driving, parking lot navigation, urban navigation, and then one of the papers that we're going to discuss next class is regarding driving styles as well. Okay, so now let me define things a bit more formally. So we're going to go back to Markov decision processes, but now we're going to consider a Markov decision process without any reward. Okay, so here I'm going to use a notation MDP/R, which means without a reward. And then so in this context, we have same components as in a regular MDP, except for the reward model. So we still have states, actions, transition model. And now I'm going to add here the optimal policy. So again, we're in a context where we're doing the inverse of reinforcement learning. So our goal is not going to be to find the optimal policy. Let's just assume that we have it because maybe we have access to an expert who can demonstrate this policy or even tell us what is the optimal policy. So now the goal in this problem, so this type of MDP without a reward, the goal might be simply to find what is a reward model that is being implicitly optimized by the optimal policy pi star. Okay, so now you might ask, like, why do we care about doing this? I mean, at the end of the day, in reinforcement learning, our goal is to find an optimal policy. And here, you know, if I tell you that we already have the optimal policy, then why do we even bother with this, right? So why should we care about finding the reward? Aren't we just creating an artificial problem for the sake of it, right? So the answer is that there's lots of problems where it will be useful for transfer learning to have, to find what is the underlying reward function. So here I've got an example. Let's say that we want to do route planning, and then here there might be several objectives where you're driving a car in a city, and then whenever you want to go from point A to point B, then you might want to optimize based on time, based on distance, based on energy consumption. You could even add maybe based on the scenery. So there's lots of reasons why you might pick a route over another one. Okay, so here it's actually not clear which route you want to pick because it depends on what is the objective. Now, let's say that we know the route or the policy that is typically followed by taxi drivers. These are expert drivers, right? And let's say that we've got this information for any pair of locations in some city. So in fact, some researchers did some work along those lines where they got some data from some taxi companies, and then the taxis, you know, they drive pretty much everywhere, so they can record what are the routes that are followed, and taxi drivers usually have a good sense of how to optimize those routes. Okay, I mean, they don't necessarily optimize always for time, but they might optimize for some combination of objectives here. Okay, so So now, if we have the route or the policy that's followed by a taxi driver or many taxi drivers for any pair of locations in city A, then it should be easy now to just have an autonomous car follow the same policy in city A, because we have already what is the optimal route, or at least some good route based on what taxi drivers do. But now what if we go to city B? So in city B now, maybe we don't have the taxi data, and maybe we'd like to extrapolate how to find a good route without having access to previous demonstrations from humans like taxi drivers. So in this case, if we happen to have instead the reward function, then we can do some transfer learning. So if we have the objective that's optimized by the taxi drivers in city A, then we can use that objective as well in city B and then optimize the routes to have similar properties. Right? So in fact, you see, as a driver, you live in a city, Waterloo, and then you're used to driving here, but now let's say you do a trip and then you go to a different country and now you have to drive over there, right? Then you kind of know how to go about choosing some routes and so on, and then you would be able to function. But now you see, we'd like to have the same thing with an autonomous car, and this is an example here of transfer learning where you would like to be able to transfer the policy, but I guess we're not going to transfer the policy directly, but instead we're going to transfer the reward function, because the reward function essentially captures the essence of how we optimize our routes. And then so in many problems, right, then it might seem simpler and more direct to simply learn directly a policy and transfer that, but it will be more general to instead learn a reward function, because that just captures the objectives and then transfers this. So if the dynamics of the environment are different, or if there are some other properties of the environment that are different, we might still want to use the same objectives, and then we can re-optimize based on that. So that's where it becomes useful to try to recover what is the reward function and therefore the objectives that are being optimized. Any questions regarding this? Okay, very good. All right, so now the question is, how do we find the underlying reward function in the problem that we just looked at? What we can do is go back to our definition of a value function. Right? So the value function, according to policy pi and reward function r, is simply the expected sum of the rewards. So I've got here the rewards, and then it would depend on the policy pi. Okay, so, and then obviously depends on the reward function. Now, finding r, perhaps we can frame this as a problem where we now have some constraints, and we're simply trying to find what might be the reward function that would make the optimal policy pi star be the one that has the highest value in comparison to any other policy, as well as in any state. Okay, so at least implicitly, this is what the problem really consists of. So it's a problem of simply finding a reward function that satisfies a bunch of constraints, where we have an inequality like this for every state and every policy. Okay, so this is not yet something practical. There are in fact several problems. So here, this problem, which you could think of as a satisfying or a constraint satisfaction problem, it will have many possible solutions. Okay, so here there will be many possible reward functions that will satisfy these inequalities. In fact, there is a trivial reward function that would just set the reward to 0 all the time, and then you can show that this inequality holds. So then we're not going to go very far with this, okay? But in any case, I mean, these are still inequalities that we would like to satisfy. We're going to have to do something about this to rule out these types of trivial reward function. So we're going to need some additional criteria, but yeah, we need to deal with this. Another problem with this here is that the way I wrote this, there's going to be one constraint for every state and every policy. So that means we have to be able to enumerate all policies. And I mean, for most domains, this is just not tractable because a policy is a mapping from states to actions. So even if we have a small state space that is discrete, a small action space that is discrete, is going to be exponentially large because for every state you can choose different actions. So the number of policies is just going to grow exponentially here. And then if we talk about continuous states and continuous actions, then we can't even enumerate the policies, right? So I guess here this was just something conceptual that I was mentioning, but in practice we need to deal with this. Okay, and now another problem is that in the way I defined the problem earlier, an MDP without a reward, I assumed that I knew the optimal policy as well as the transition model, right? So if I just go back, right? So here I assume that I know the transition model and that I know the policy. But in practice, I might not have these things, okay? So, I mean, the point of the course is that we're talking about reinforcement learning, where in general, we do not assume that we know the transition dynamics, right? So here, we shouldn't assume that either. Okay, so to deal with those problems, I guess an alternative formulation that does correspond really to what is inverse reinforcement learning would work as follows. So you have states and actions. Now we're not going to assume the transition model, so that's why it's grayed out. We don't have the reward model either, so that's why it's grayed out. And okay, we have a discount factor, we have the horizon, and now the other thing I'm going to assume that I have access to is going to be some expert trajectories. So expert trajectories are just going to be sequences of states and actions. And here I've got one sequence that goes up to the horizon h. I've got a second sequence that goes up to the horizon h, and so on. Okay, so imagine that you have several sequences. In the context of autonomous driving, it might be that you have a taxi driver that you observed the path that he or she has followed to go from point A to point B. So this would be one sequence, right? In the context of robotics, like let's say a quadrator, then it might be that you want the quadrator to perform a certain maneuver. So then it would go from a certain pose to another pose, and then the sequence of poses in between would be the trajectory. Okay, so yeah, so here you see we're not assuming that we know the optimal policy. We just assume that we have a sequence of state action pairs that correspond to presumably a good policy that comes from an expert. And there's lots of situations like what we discussed before where we can obtain those. And then the problem again is that we find the reward model that the expert trajectories are implicitly optimizing. Okay, so here we observe those trajectories. We don't know for sure how or why the expert chose these actions at every step, but we assume that there's some underlying reward function that the expert is really optimizing. Okay, yeah, so that's a more realistic description of the problem. And now we could ask again, since we have the expert trajectories, why not find a policy by supervised learning instead of just finding R, right? Because here you see, in general, the goal of reinforcement learning is to find a policy. Now, I'm not assuming that I have the policy, so perhaps I could just make that the goal. Let's find the policy, because ultimately that's really what we're after. We're going to try to find a policy in some setting. And then we have sequences of states and actions, and then here we assume that these actions come from an expert, right? So we could just do supervised learning, where we train a policy network to produce the action that correspond to the expert action in each state. And then we would, in that sense, be able to mimic what the expert does, right? So we could do this. And in fact, this has been done in many situations, and it will mimic. I mean, it will learn from an expert. But if you recall, for instance, when we looked at the paper for some of the early versions of AlphaGo, right? So AlphaGo was initially trained by supervised learning from expert trajectories, right? So there were all these expert matches where for different board configurations, some expert indicated what move they would choose, and then AlphaGo was trained to select actions based on that. Now, if you recall, the drawback of this is that then AlphaGo would have been kind of never much better than the experts themselves, and some of the experiments showed that, in fact, it was slightly worse, right? So it wasn't able to perform better. So that's why this in general will never be something perfect. And then so, yeah, either we would like to be able to improve beyond what the expert is doing, or in some situations as well, we would like to be able to transfer to other settings. So for transfer learning, so here the idea is that the policy that we could obtain by supervised learning will work obviously in the current environment, but now what if we want to transfer this to a new environment where the dynamics, so the transition function is slightly different. We don't know what it is, but it's not exactly the same, right? So then you're better off just finding the reward function R, and then using that as your objective, optimizing a new policy by reinforcement learning in that new domain. Okay, so that's why, again, going through this trouble of finding R is valuable here. Any questions regarding this? Yeah.
So, in terms of the last point, does that mean in a new domain you have to model the state space such that this state space is similar to the original?
Right. Oh, good question. Yeah. So in the new model, do we assume that the states are the same or not? So in fact, here we don't have to assume that. Okay, so we're going to learn a reward function, right? That's our goal. The reward function in theory depends on states and actions, but what you can do in practice, and that's what I'm going to show you in the next few slides, and also the papers we're going to discuss next class, is that what is common to do is to extract features from those states action pairs. And the idea is that maybe the states definition are going to be different across different domains, but then if the features are the same, then it's okay. So then we can work with a reward function that depends on features, and then at that point it doesn't even matter, like the states could be different in different domains. Okay, so in this context here, yeah, let me define a reward function that depends on some features. I'm going to denote those features by phi I. And concretely, the reward function might be a linear combination of the features, or it might be some nonlinear combination, maybe that's represented by a neural network. Okay, so here it would be a neural network that takes as input the features, and then it has some weights that would combine them according to some computational graph, and that produces as an output the reward. Okay, so let's assume that our reward function, the underlying reward function, can be represented by something in that class of models. Now, one idea for finding the reward function is that what we could do is update R by revising the weights that define the reward function. And then based on this reward function, now let's find a policy pi, and then let's make sure that this policy pi will not perform any better than what we've observed from the expert. So the expert, produced some trajectories, and we need to make sure that those trajectories are going to remain the best ones, okay, that they'll earn the highest reward possible according to the reward function. So when we find a new policy pi, we're going to check how that policy compares to the trajectories of the expert. And then the idea is that in general, if we find a pi that optimizes R, it's going to be the best policy for that reward function, and chances are it's going to have a value that's higher than what the expert trajectories are producing. So then it will mean that we need to go back and revise our reward function so that now we can make this new policy look like it's worse than the expert trajectories. So I'm going to show you on the next slide some pseudocode, but for now, yeah, the idea is that we're going to alternate between these two, where we're going to update or compute a reward function. Based on this, we're going to see what is the best policy, and then we'll want to verify if that best policy is better than the expert trajectory. In general, it will be, which means that we're going to have to revise the reward function until we cannot find any policy that would be better than the expert trajectories. Okay, so here's some pseudocode. So this pseudocode is based on some work from Abil and Nguyen in 2004 that they call Apprenticeship Learning. So here, let me index features by I. I'm going to index some trajectories by J, and I'll index some policies by K. So initially, I'm going to start with some policy at random, so just some arbitrary policy. Now the goal here is to find the reward function and also some policy, but really it's to find the reward function. What we do is now we go through this loop where we alternate between the two steps that I mentioned before. So this first step here is where we're going to revise the reward function, update the reward function, and here the reward function is really defined by a set of weights W. Right? So if you recall, here I'm assuming that the reward function is either a linear reward function with respect to some features or something nonlinear where there's some weights, as in a neural net, that defines the reward function. So in this step, I'm going to solve an optimization problem that will allow me to find a new reward function that's determined by W. So here I'm going to find a reward function parameterized by W that maximizes this difference. Okay, what is this difference? So here I'm taking the example of a linear reward function. So if my reward function is linear, then I just have a weighted sum of the features. And then in particular, here I'm going to compare the rewards that are obtained by the expert when we simply plug in the actions that come from our trajectories. So here you see we have some trajectories. These are alternations of states and actions, states, actions, states, actions. So we can simply look at what are the rewards that would be earned based on this linear reward function if we just focus on the actions that are chosen by the expert according to the trajectory. Okay, and then what we would like to do is to make sure that now our reward function will show that whatever the expert chose is at least as good, in fact, much better than what any other policy would choose. So here I could look at the sequence as well of states that are obtained by executing a different policy. So here, instead of looking at the trajectories themselves, I'm just going to look at the states and then replace the actions by whatever the policies would choose. Okay? So if I choose some different actions, then I will obtain here some different rewards, and I want to make sure that this is greater than the rewards that are earned here. Okay? So now I simply want to maximize the minimum difference. So here the minimum is with respect to the different trajectories as well as the different policies. So I simply want to come up with weights that would maximize this difference. And then I will return those weights as my new policy, as my new reward function. But now, when I get this new reward function, just as a sanity check, let me find a new policy, pi k, that is optimal for this reward function. And then at the next step, right, we would like to verify if that new policy would earn some rewards that are higher or not. Okay, so in general, if we can arrive at a point where there's not much difference between the best policy found here and then what the expert trajectory gives us, then we will assume that we've now found a reward function that could explain well what the expert is doing. And so this scheme is interesting because now we don't have to enumerate all policies, right? So it's an iterative scheme where we simply generate policies, one at each iteration, and then simply verify after that that the reward function will make sure that the expert trajectories give us rewards that are at least as large as if we executed the expert as if we executed the some other policy. Okay, so that's the algorithm in I guess in a very brief explanation with some pseudocode. And yeah, I'll take some questions. Any questions regarding this? Okay. So, all right, very good. So then, yeah, I did not include any examples of this because next class we're going to have some papers that will show some examples for that. So we're going to see some application in the context of autonomous driving. But in any case, this was some foundational work that was done in 2004, and several other papers have built on this idea. And then so next class we're going to see one paper that discusses concretely some variant of this. It won't be exactly this, but some variant of this. Yes? How do we extract the features? So here, I guess we're going to assume that we already know what features we care about. So for instance, in the context of autonomous driving, you could imagine that there are some features about simply the number of turns, how many times you change lanes, and things like this that could characterize maybe the driving style. Okay? And then we would like to have now some reward function that will depend on this, and we're just not sure how people would prioritize, let's say, lane changes over turns over other aspects of driving. But the idea is that, yeah, the features here assume that they are provided already, so there's a domain expert that will come up with the feature function, all the phi's.
So they are handcrafted?
Yeah, they are handcrafted. Yeah. Mike, did you have a question? No? That's good? Okay. All right. Okay, so let's stop here. And then, yeah, next class we're going to see some concrete examples of this in the context of autonomous driving.